Welcome back, everyone, to week 2 of extended e-learning. We're still going to continue down this discussion of power series. And last week we introduced you to the terms interval of convergence and radius of convergence, and you had to find the interval and radius of convergence of certain power series. One of those earlier videos, we also introduced you to a very important power series. It's the geometric power series. So it's based on the typical geometric series, the series whose common ratio is any number. And in this particular one, we want to think of the one that starts with the number 1 and then multiplies by r. And if the ratio in this geometric series is between -1 and 1, we know that that's a converging geometric series, and we know what it converges to. It converges to the first term, which in this case is a 1, divided by 1 minus the ratio. And what we'd like to do here is let's just take that concept, and instead of calling the ratio r, let's call the ratio x. And the series becomes 1 plus x squared, and on, as long as the x is between -1 and 1. This is going to be, again, a converging geometric series, and it converges to the quantity of the first term, 1, divided by 1 minus x. Now that, to us, looks just like what we would call a function of x. And so we want to think of this now and kind of flip this equation around and say that, oh, well, for the function f of x is equal to 1 over 1 minus x, as long as we're in the interval of convergence, -1 to 1, that can be represented by this power series that's written up there. Actually, it starts at 0. And so x to the power k, which generates this. Basically, you want to think of it as an extremely long, infinitely long polynomial. Okay, so this geometric power series, which is the power series for the function 1 over 1 minus x, you're going to be using this a lot today, along with a couple of theorems about combining power series to make new ones. But a lot of it will be based on our knowledge of this geometric power series. So the bulk of our lesson and examples today are going to be to generate new power series using existing power series that we may already know of, using the theorem that's outlined on this slide. Essentially what it's saying is that we can combine, if we have a power series for two different functions, maybe f of x and g of x, and they each converge on their own interval of convergence. Now in this theorem, we're going to presume that the interval of convergence for both of those power series is the same, and we're just going to specify it as the name I for interval. What the three parts of this theorem say is that I can add, just like I can add two functions together to make a new function, I can add their respective power series together and create another power series for the function made up of the sum or difference of those two functions. And just like I can multiply two functions like f of x times g of x, I could multiply their power series together and create a power series for the product of the two functions, f of x and g of x. The third part is a composition. And let's suppose that f is our primary function and we have a second function h. Now the form of this function h is going to be required to be a monomial of the type where there's a coefficient times some power of x. And now we're going to perform a composition f of h of x. And what this part says really is that I can do the composition into the power series instead, just like you would if you were doing the composition f of h of x. What you would be doing is you would have the expression for function f, and everywhere the x appeared, you would put the expression for h of x. And what the part 3 of the theorem says is I can do that same thing and in my power series replace the x with the expression h of x. And you're going to see us use all 3 of these at some point in the examples today. One where we multiply, one where we add, and one where we do compositions. Maybe sometimes we'll have to do maybe more than one at the same time. So in the examples today, we're going to start by reminding you of that geometric power series for the function 1 over 1 minus x. It's the power series 1 plus x squared plus x cubed, and on forever. This is a converging power series. In fact, this power series converges to the function 1 over 1 minus x as long as we are in the interval that contains all the values of x between -1 and 1. So here it's said a little more compactly, but what this is really saying is that the interval of convergence is all numbers between -1 and 1. Okay. Now, what we're going to try and do is come up with a power series for this function, x to the 5th times 1 over, x to the 5th divided by 1 minus x. Now, to use some of the theorems outlined in the previous page, I would like you to think of this one as the product of x to the power 5 and then that function 1 over 1 minus x. So what's nice here is that if we can write the power series for this function and think of that as a really just an infinitely long polynomial, we can really just multiply in and distribute out that x to the 5th. Okay, so there's 2 ways you can do this. I like to first just work with the polynomial itself. And so in one hand, we could take this and take x to the 5th, and then I would write out the first few terms of my power series for 1 over 1 minus x. And I would do that at least a few terms there. What I actually like to do is just kind of dot, 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 and put the general term in there too. Okay, so it's just going to keep going after that, but the general term was x to the k, right? And now, if you imagine that this is just treated like a polynomial and we're multiplying it all times x to the 5th, then I'm going to write out what we're trying to build it to here. And the part we're substituting for is this 1 over 1 minus x is going to be changed to this polynomial. But now, let's just distribute out this x to the 5. So each time I multiply it in, the power goes up by 5. So it's going to start being x to the 5, x to the 6, x to the 7, and on. And by the time you get to that general term, you think of it, you just have to add the powers together, and you can actually get the general term for this new power series here, x to the power k plus 5. So in fact, what we can just do is compactly write this as power series starting at k equals 0, and the general term is x to the k plus 5. So it can be expressed either this compact way or kind of back up one line earlier where I actually had the terms written out. What we're ultimately going for, I think, is just this general compact summation expression here. So our next example is similar in that we're starting with that geometric power series again as our basis for this one. And we're modifying it a little bit this time, but not by multiplying. We're actually going to change that x to 2x. So we're looking for the function 1 over 1 minus 2x. Now, here's where we could use the notation of the theorem, in that if we think of this geometric power series as your function f of x, either in the form 1 over 1 minus x or in its power series form over here, you could now think of this where let's call g of x the function 2x, and that way this could be thought of as f of g of x. In other words, f of 2x, because everywhere the x is in the original function f, you now have a 2x. And so you're really doing a composition here. And so the way this works is we can make that composition also into the power series for f of x. So how we're going to do this is this. Instead of writing the power series for the function f as 1 plus x squared, I'm going to write it out and leave a little blank where the x would normally go, because it's going to be a composition where the quantity is now going to be changed to 2x. Right? So this is a composition into that long polynomial where all the x are changed to 2x. And now if you think about the general term, it used to be just x to the k. Well, it's now going to be, the general term would be 2x to the k. So if I wanted to write it out without all the parentheses, we definitely could. I'm just going to take a little bit of time to do that here. And so that way now, this last general term, it actually probably is easier to leave the parentheses there. And so my power series in compact form is now going to be this, from k equals 0 to infinity. And really just instead of x to the power of k, all we're doing is the composition, and now it's going to be 2x to the power of k. Now, this is a good time to bring up what the interval of convergence is, because in the original power series for f, the interval of convergence is the numbers between -1 and 1. The interval for this function for f is -1 to 1. That's not necessarily what it is now in this composition. What the theorem says was that this converges as long as the values of g of x are within the interval of convergence for f. So what we have to do to find the interval here is to make the composition also there. So instead of x being between -1 and 1, what has to happen now is 2x has to be between -1 and 1. So if I have to divide by 2 to get the actual interval, and that's actually now going to be just between -0.5 and 0.5. So I'm just going to circle here the interval of convergence, and here's the general formula for the power series over here. So here's part C, again reminding you of the geometric power series for the function 1 over 1 minus x. And I'm again just going to refer to this as f of x, so that I can refer to this one we're going to build as a composition. Now notice it's 1 over 1 plus x squared. Two things changed here. X is now x squared, and that minus changed to a plus. So what I think we want to do first to see the composition correctly is actually write it like this. 1 over 1 minus something, and now that something would be called negative x squared. Now after I've done that, this is going to be a lot like the previous problem. So if I want the power series for 1 over 1 minus negative x squared, all I'm really going to do is take the power series for 1 over 1 minus x, that geometric power series, and once again, I'll leave some blanks wherever the x would normally go. Including the general term, and we're going to replace all those with the quantity negative x squared. Now what you're going to notice this time is this is going to create ourselves an alternating series here. So if I remove the parentheses, every time I have an even power around the negative x squared, I'm going to get a positive term. Anytime I have an odd power, I'll still have a minus sign. So it's going to end up kind of going like this style here. So how I'd like to write this general term is this. The x squared to the power k, that's of course going to be where you multiply the powers and get x to the 2k. So that's how you're getting x to the 0, x to the second, x to the fourth, x to the sixth. Now, there's also a negative or a -1 there, and that is also being raised to the k, and that's where I'm going to get my alternating sign from, right there. And so my general term is now going to be that when k goes to 0, starts at 0 and goes to infinity, my general term is now this alternating series, -1 to the k, x to the 2k. Okay? Now, my original interval of convergence was that x had to be between -1 and 1. So what has to be true now is that x squared, sorry, negative x squared has to be between -1 and 1. If you think about that, if x is in fact between -1 and 1, x squared will definitely be 2. So it looks like the interval is still going to be the same. X can be between -1 and +1, and that would then cause x squared to also be between -1 and +1. So the interval stays the same here. Well, this wraps it up for today. Next time we're together on Wednesday, you'll be modifying power series using calculus, things such as differentiation and integration to create new power series. So for now, you'll work on problems only having to do with basic things like multiplying, adding, subtracting, and the composition you saw here in examples B and C. We'll see you back here on Wednesday.